Let's just wait for a couple of more minutes, see if someone joins, and then we'll begin. So hello everyone. I couldn't take the class on Tuesday as I wasn't feeling well. So I'm Tanya. I'm one of the TAs assigned to the aircraft design course taught by Professor A.K. Ghosh. We'll go over the contents of week 8, the questions, and then do a few questions that will help you solve the week 9. Okay, so the first question was, a commercial airplane is landing with touchdown velocity of 285 km per hour. The stall velocity in meter per second during this maneuver will be. It's fairly simple. They've given you the touchdown velocity, and we know the approximation that we take. What was the approximation? Touchdown velocity and the stalling velocity. What was the relation? We touched down 1.1. I think in the solution manual they've taken 1.15. So that's 1.15 we stall. They've asked you what the stalling velocity is. So we stall is we touch down 285 by 1.15, and this value is 247.8 kilometers per hour. And they've asked you meters per second, so just convert it to meter per second, multiplied by 1000 divided by 3600, and you get the value. You get 68.84. Right? Meters per second. So that is the answer. The next question, if the thrust to weight ratio of an airplane is given and the aerodynamic efficiency. What was aerodynamic efficiency? Aerodynamic efficiency was the lift to drag ratio, right? So L by D is given. T by W is given as 0.05 and L by D is given as 10. They've asked what the approach angle is. We've studied the relation for the climb angle or the takeoff angle. Similarly, analogous to that, you have the approach angle relation. What was the relation? It'll just be, instead of, so what was the takeoff angle as a climb angle? Sine gamma, what was it equal to in terms of T by W and L by D? What was the equation? Yes. So the reverse will be, or the negation of this will be the approach angle. Sine of theta approach. So yeah, so it'll be, and then you take that L equal to W and substitute it, right? So it was initially sine gamma was T by W minus d by w, and then you take lift equal to weight, so then you do minus d by L, and then you get this relation. So this is true for the approach angle, that is 1 by L by D minus T by W. So they've given you both of these quantities, that is 1 by 10 minus 0.05 comes to 0.05. So theta approach is sine inverse of that, and that comes to around 2.8 degrees. 2.8 degrees. Okay. So let's go to the next question. If the thrust to weight ratio of an aircraft is 0.05, so the same values are given. The aerodynamic efficiency is 10, and they've given a turn radius here for a pull-up maneuver. So they've given R. That is the extra information available. R is equal to 50 meters, 500 meters. What will the flare distance of an aircraft be? Again, the straightforward formula. What was the formula? Flare distance, SF was it was just R and sine of the approach angle. This was not discussed in the class? Okay, so when you have a pull-up maneuver, okay, it should not be approach angle. So that angle, okay, I don't have the figure with me right now. Just a minute. Okay, flare distance I think is when you get into that pull-up from the ground. I'm not very sure how we derive this formula. So, sorry. I couldn't catch your voice. Okay, so I believe it's like when it's coming to touchdown, but you have to pull. Yes, your voice is breaking. Can you speak? I can't hear you. I believe that it's when we come to touchdown, and then due to some reason you cannot, and you have to pull up. So you have to turn radius there. I think the distance required to successfully complete that maneuver is what this is. Not very sure what it is. I will get back. How much is the distance that is allowed to do this? I'm not sure. I'm, I'll get back to you on Tuesday. Okay. So we'll get back to this question on Tuesday. Then, to execute a takeoff maneuver, which are the control commands that are required? I think we've discussed this in one of the previous weeks. What would the right answer be? Is it just the elevator and rudder, elevator, aileron and rudder, aileron only, elevator, rudder? Okay, so we know that it requires throttle, obviously, to pull up. We know it requires elevator to have the pitching angle in order to for it to climb. Why do we require the rudder? It is the fourth option, that is right. Why do we require rudder? Any? Sorry, I didn't hear. To maintain the what angle? I can't hear either of you. Is it a problem with my connection or yours? Am I audible clearly? Okay, can you try answering that again? I didn't hear you. Why won't it maintain its line if we don't deflect the rudder? If ideally if it was at neutral, if there is no deflection right or left, and you just have elevator and throttle, it should take off, right? It should take off in a straight line. Why would it? Why would you want to deflect the rudder to maintain the straight line? Your voice is breaking. I'm not able to hear at all. Can you maybe put it in the chat box or something? It is right. You are right that it is to maintain the straight line. But why won't it remain in the straight line? We don't have. There may be gusts or crosswinds on the runway. If I say there is no gust, in the absence of gusts or crosswinds, even then we employ the rudder. Why? During takeoff. Think about it, take a minute or two to think about it. We do deploy the rudder even if there are no gusts or why? Can you think of any forces that act that will try to maybe yaw the aircraft or roll the aircraft? Anything that disturbs it from its straight line? Okay, so what is the power plant of this aircraft? It power like propeller or the jet engine, you have some rotating parts, right? Is that some sort of a clue? Think about it. When they say throttle, there is a power plant. Can you think about some reason? So when the power plant or the propeller of the jet engine, propeller of the propeller aircraft, or the blades of the jet of the compressor rotate, they rotate in a particular direction. Usually it's in the clockwise direction when you view it from the cockpit. Okay, so in you viewing in that direction, it's usually in the clockwise direction. Now all of your engines have blades rotating in the same direction. There will be a net torque, right? Yes. So the uneven engine thrust while starting. Yes. So there will be a net torque. To negate that, we deflect the rudder. Another may occur is something known as spiraling slipstream. So the yellow line that is shown here is, again, the propeller is in the front. It pushes the wind across and around the fuselage, around the body of the aircraft in such a way that it impinges on the tail at some point. In this figure, it's shown to be impinging in this direction, but it may also happen that it comes on this direction. Correspondingly, you need to deflect the rudder so that it maintains a straight line. It maintains the path along which it has to take off. Okay, there could be several other reasons, but these are two reasons which I thought would be more significant in telling you why we need to deflect the rudder. Okay, so one was the net torque because of the power plant. The other one is the spiraling slipstream. Slipstream is the gust of wind, not gust, you can't call it gust, but the stream of wind, stream of air that is pushed behind, that spirals around the fuselage and the body of the aircraft and finally impinges on the vertical tail. Okay. Okay. So next question was for the jet powered aircraft. Here I think we've discussed this question before, and here there was jet powered civilian aircraft. I think we had discussed this in the first class. It should have the word civilian there, otherwise it is ambiguous. Okay, so let's proceed with civilian. I'm not sure if they will look into it, but I will put it across to the TA. So for the jet powered civilian aircraft, the thrust to weight ratio of an aircraft in climb flight will be. So the climb equation is the same. So sine gamma Let's thrust to it. 1 by L by D. Just a second. 1 by L by D, and they've asked you for thrust to weight ratio. That is sine gamma plus 1 by L by D. Typical values, maximum value of civilian aircraft climb angle would be around 20, 25. So take sine 25, and the maximum value of L by D that I've found was again 25, and this is less than 1. Okay, but if it becomes like that was mentioned in the forum, if this word civilian is not mentioned, then you have situations where it goes greater than 1 for fighter aircrafts. Okay, so I will put it across to the concerned TA to revise the question, revise the marking scheme. Okay. Okay, so I will just send. So both are jet, civilian and fighter, both are jet. The power plant there is, I mean, it's jet, right? So that is not the problem here, but they should have mentioned either civilian or fighter. So I will bring it up with the concerned TA. Maybe he will reevaluate this class question or not consider it. We'll see what can be done about this question. Okay. Moving forward, we'll just do a quick revision of the stability of the pitching moment stability in that in the longitudinal direction. So static stability is the initial tendency to go back to equilibrium. How is it different from dynamic stability? Why do we specify static stability, and how is it different from dynamic stability? Okay. Correct, exactly. So for dynamic stability, the aspect of time is brought into the picture. That is the difference. Okay, you're absolutely right. Static stability is the initial tendency, whereas dynamic stability is over a period of time, whether or not it will go back to equilibrium. Okay, so for a pitching moment, in the equation we have is Cm is Cm naught plus dCm by d alpha into alpha. This is the linearization approximation that we consider. And for static stability, like we had mentioned several times over the course of the few weeks, is that for static stability, for longitudinal static stability, the only condition we have is that dCm by d alpha should be less than 0. So your graph should be something like this, Cm versus alpha. Another condition that we see is that Cm naught should be greater than 0. The only reason why this should be greater than 0 is to trim the aircraft at a positive angle of attack. So now if you have something like this, if Cm and alpha, this is still a stable aircraft, but the value of alpha at trim is negative. Here the value of alpha at trim is positive, which is what we desire. We wish to trim the aircraft at a positive angle of attack, which is why we need Cm naught to be greater than 0. Okay, so this is not a condition for static stability, longitudinal static stability. The only condition for longitudinal static stability is Cm alpha should be less than 0. Okay, now the two contributions, that is contribution from the wing and the tail towards this overall Cm. So we write both of these contributions again in terms of Cm naught and Cm alpha. So the contribution of the wing towards Cm naught is denoted by this parameter. So that is Cm naught wing and this is Cm alpha wing. Similarly for the tail, we have Cm naught tail, and you have including the negative sign, you have Cm alpha tail. Okay, so now from these equations, can you try to tell me if the wing is stabilizing or destabilizing in terms of longitudinal stability typically? So you only have to consider the Cm alpha terms for stability to comment on the stability. So Cl alpha is positive, right? We either take a symmetric airfoil or a cambered airfoil. Either case, Cl alpha is positive. This quantity is positive. What about this quantity in the brackets? XCG minus XACW. For typical aircrafts, will it be positive or negative? Can you try to comment on that? Positive. So the overall Cm alpha contribution of the wing is generally positive. So is it stabilizing or destabilizing? Destabilizing. Now let's come to the tail contribution. VH is the tail volume ratio. So VH, I think I've put it up in our next slide, but I'll just write it here. What was VH? Does anyone remember? Tail, horizontal tail volume ratio. So what was the formula? We had used this in a couple of numericals. Okay. So it was the area of the tail by, yes, S C bar. Yes. And this is of the wing. Okay. Where ST is area of, SW is area of the wing. LT is the tail moment arm. So that is the distance between the aerodynamic center of the tail and the CG. Something like this. Okay. Akin to this. And CW is the mean aerodynamic chord of the wing. Okay. So this term, will it be positive or negative? The areas are positive, chord is positive, this T positive, exactly. So this will be greater than 0. So this is positive. Now eta. Eta is, what was eta? Tail efficiency factor. What was the formula? Yes. At the wing. Correct. So this factor, will it be positive or negative? It will be positive, right? So their velocities. Positive. Again, CL alpha tail, positive. And this downwash angle, the rate, the slope is typically less than 1. It's always less than 1. So this quantity will again be positive, right? So this overall quantity, because of this negative sign here, will be less than 0. So does the tail contribute towards stability, or is it destabilizing? Stabilizing, yes. So now we see why we need a stabilizing component, why we introduce the tails. Okay. So the question that I've asked here is, how do you ensure Cm not to be greater than 0? One point we had discussed in the previous lectures. What was that? I can think of two reasons. Can you come up with what they are? How can we ensure Cm naught to be positive? That is the overall Cm naught. How do you ensure it will be positive? Okay. So to ensure that it's positive, we require Cm naught wing or Cm naught tail, any of them, like preferably both of them to be positive. So one thing we can do here is that you play with this tail setting angle and wing setting angle and ensure that this entire quantity is greater than 1, greater than 0, right? This is usually less than 1. So just play I wing and I tail. That is the wing setting angle and the tail setting angle to ensure that this Cm naught tail is positive. That is one way. What about when you look at the wing contribution towards Cm naught? What can you do there? This quantity is negative. You can't do anything about that, right? Because the CG is typically behind the AC of the wing. So what else can you do to ensure that Cm naught is positive? You can't do anything about this term. What can you do? What can you do? You can make CMAC at the wing positive. How do you do that? How do you do that? What is CMAC at the wing? How does it come? What is this term CMACW? Of the wing, yes. So for a symmetric airfoil, what is CMACW? Yes, for a cambered airfoil, positive. So how do we ensure for a cambered CMAC? For a cambered airfoil, CMAC. Okay, so this is your cambered airfoil, right? So this is your AC. And for a cambered airfoil, your center of pressure is behind, right? So when you transfer the aerodynamic forces, lift and drag, it comes with a pitch down moment. So CMAC at the CM at the aerodynamic center for a cambered airfoil will be negative. So we typically use cambered airfoils for the wing. So this will be negative. What can you do to ensure that the CMACW is greater than 0? Exactly, reflex airfoils. So we can use reflex airfoils. So two ways that you can ensure the overall CM naught is greater than 0 is to have the wing setting angle greater than the tail setting angle. Wing setting angle greater than the tail setting angle. Or, or, and you can have CMACW greater than 0 using reflex airfoils. These are the two ways in which you can ensure that you can trim your aircraft at a positive angle of attack. Okay. The next concept that was discussed was a neutral point. Neutral point is like the aerodynamics. So aerodynamic center of a wing and the neutral point of an aircraft are analogous. Okay. So it's the same. If it's just a wing, it is the aerodynamic center. If it is the entire aircraft, it is neutral point. So neutral point of a, if someone says neutral point of a wing, it is nothing but the aerodynamic center. Okay. So now the formula that we used to calculate that was given here, where XACW, there's a bar above, so that means it's divided by the mean aerodynamic chord, and the quantity which represents the stability of an aircraft is given by static margin. Static margin is the negative of the slope of the CMCL curve. Okay, so for a stable aircraft, will static margin be positive or negative? Positive. For a stable aircraft, a statically stable aircraft, this will be greater than 0. So that means the CMCL curve will have a negative slope, right? So the CMCL curve, just like the CM alpha curve, CMCL will have a negative slope, okay? Which is why this quantity will be positive for a statically stable aircraft. Okay, these are just some formulae that we may use in our numericals. We've studied the VH, that is the horizontal tail volume ratio. So ST upon S, LT upon C bar, where LT is the tail moment arm, that is the distance between the aerodynamic center of the tail and the CG of the aircraft. The downwash angle epsilon is represented by linearized representation is dou epsilon by dou alpha into alpha. This alpha, you must remember, it's alpha of the wing. Okay, so epsilon naught is given by this formula and its slope is given by this formula. Now we need to remember this conversion between 3D and 2D. Okay. Sorry. Okay, now let's do a few questions. I think we've done something similar in one of your assignments. So an aircraft wing has a positive cambered airfoil. Which of the following graph correctly represents the relation between CL and alpha? Which one will it be? Let's A. Okay, first one. And why? Why did you say it's the first one? Okay. And what about B? What kind of airfoil is B? Uh, okay. This one is B. This is negative camber, right? This is for symmetric. Okay. Okay. Next question. An aircraft is having a rectangular wing with a wingspan 3.5 meter and chord 0.25 meter. So you have wingspan is 3.5 meter, chord is 0.25 meter. The horizontal tail volume ratio, that is VH, is 0.57. What should be the length of the tail arm, LT, of the aircraft? Assume that the tail area is 25% of the wing area. So ST is 0.25 wing area. How do we proceed with this? How do we start the calculation? We need to find the tail moment arm. What formula do we use? We just discussed this formula in the previous slide. Yes. Into C bar. So you have all of those terms. Only thing missing is LT. LT is VH into SW upon ST and C bar. So let's just calculate this. VH was 0.57 into SW upon ST is... Okay, let me just complete this. Yes, 0.57. 0.57 meters. Okay. Next question. The aerodynamic center of a horizontal tail from reference line is 1.1 meter. Tail arm distance LT is 0.68 meter. What is the location of the center of gravity of the whole aircraft from reference line? So basically they've asked you for XCG. They've given you XAC tail, right? And they've given you LT. So if you take this to be your fuselage reference line and you take some reference point, it's usually the leading edge of the wing, but it can be any reference line. And you suppose you have your wing here and you have your tail here, and this is your CG. So what they've given to you is aerodynamic center of the horizontal tail from reference line. So this is given as 1.11 meter. Then they've given you LT. LT is the distance between XCG and, so this is AC of the tail. They've given you this as 0.68 and they've asked you to find out this distance, that is XCG. How do you find that? How do you find that? It's just the difference between these two, right? 0.68. How much is that? Meters. So that is this one. Okay. Next question. What will be the value of Cm naught at CL equal to 0.22 for an aircraft flying at CL trim 0.66 and static margin of 10%? Just read this question carefully for some time and then tell me how to proceed. How do we proceed with this? Just read it carefully. When they say Cm naught, what do they mean? What is Cm naught? Okay. So our equation for Cm naught, how we defined Cm naught was Cm alpha into alpha, right? So this is Cm naught. Correct? This is the quantity that we need to find. Now just think about how we'll proceed to find this. They've given you CL trim and CL naught and they've given you static margin. How will we proceed? Just take a few seconds, read it carefully. They've given you CM and CL values, but our CM naught term appears in the CM versus alpha relation. So let me just draw the CM versus alpha graph. CM alpha for a stable aircraft. Is this aircraft stable or unstable? With the given values, what can you say? Is the aircraft stable or unstable? Okay, so our line would be something like this. Okay, now if I were to draw CM versus CL, it will follow the same pattern, yes, but will this value and this value be the same? So this value is your CM naught, correct? From this equation. Will this value and this value be the same? That is the question. They follow the same trend. Yes, CM alpha, CM versus alpha and CM versus CL both have a negative slope for a stable aircraft. But is the intercept the same? This CM naught and this intercept, is it the same value? Okay, let's try that. I'm just writing the equation in terms of CL. Okay, so let's take, for now, let's just take it as a different quantity. We'll see if it's the same or not. Okay, CM naught 2 plus dCm by dCl into CL. This equation is right for this graph. Yes, okay. Let's proceed. Let's expand it. Try to equate it to the first equation. So this is equation 1. This is equation 2. From these quantities, let's try to equate it to the first equation. So let's expand this. That will be CM naught 2 plus dCm upon dCl. CL is CL naught plus CL alpha into alpha. Correct? Just correct me if I'm going wrong anywhere. Okay. Let's proceed. Now, if you take terms that are dependent on alpha and independent on alpha, separate them. So what do you get? You get CM naught 2 plus dCm upon dCl into CL naught. This is independent of alpha plus dCm by dCl into CL alpha alpha. Correct? Now, if you equate it to the first equation, okay, what will it be? It will be CM naught plus CM alpha into alpha. What do we get here? CM naught equals CM naught 2 plus dCm by dCl into CL naught, and CM alpha equals dCm by dCl into CL alpha. Correct? Yeah, take a moment to go through this equation. So does this quantity equal this quantity? For a symmetric airfoil, it will be the same, but for a cambered airfoil, will it be the same or different? This CM naught and this CM naught 2. different. Okay. So now in this question they've asked you to find out Cm naught, that is this quantity. So Cm naught is Cm naught 2 plus dCm by dCl into Cl naught. We have this quantity, we have this quantity. We need to find out Cm naught 2. Then you get Cm naught. So this is the equation that we need to use. Okay. So how do you find out Cm naught 2? How do you find out the intercept of this equation, of this line? How do we proceed? How do you find out Cm naught 2? Okay. Uh, dCm by dCl is the slope of this equation, right? Slope of this line. What is dCm by dCl from the question? What is the value? Yes, so it is minus 0.1, right? From the question. Now, from the graph, try telling me the equation for this. We'll take these 2 points, right? Take these 2 points and try to formulate an equation, y2 minus y1 by x2 minus x1, straight line equation. What will it be? The slope of this line. This is point number 1, this is point number 2. Y2 minus y1 by x2 minus x1. What are the values? Y2 minus y1 by x2 minus x1. In our case, it will be, what's on the y-axis? Cm. Cm2 minus Cm1 by Cl2 minus Cl1. What are the values? What is Cm2? What is the value of Cm at point number 2? 0. And Cm1 is? Cm1 is? Exactly. Cm02. And Cl2 is Cl trim. Yes? So that's Cl trim. Exactly. And Cl1 is 0. So from here, what is the value of Cm0? Cm02. It will be 0.66, 0.066. Yes? Yes. Substitute this into this equation. Okay, let me just, okay, let me write it down here. Where do I write? Let me erase this. Okay. So here, if you substitute it, Cm02 is 0.066 plus dCm upon dCl is minus 0.1 into Cl0 is 0.22. So the final answer is 0.044. Yes? Yes. Okay. So the point of consideration here is that this Cm0 and this Cm0 are not the same if you have a cambered airfoil. If it's a symmetric airfoil, your Cl0 will be 0 and your Cm0 will be Cm02. That is, the y-intercept of the Cm alpha graph and the CmCl graph will be the same. But if you have a cambered airfoil, your y-intercepts will change. So when you're given the value Cl, you need to remember this relation. Okay, so both the y-intercepts are not same even though they follow the similar trend. Value is not the same. Okay. Okay. Let's just try doing this again. So it will be minus 0.1 is equal to minus cm naught 2 by 0.66. Yes? Okay. So cm naught 2 will be 0.066. Okay. Any other questions with this problem? So only thing you need to remember is that this cm naught and this cm naught are different. They're not the same quantity. For a K-bird F-file, if it's symmetric, it will be the same. So these two equations, though they follow the similar trend, values, the intercepts are not the same. Okay, the slopes are also not the same. Okay, so the slope for this curve is dcm upon dcl. The slope for the previous curve is dcm upon dcm upon d alpha. The slope will be different. Okay. Okay. Next question, x bar np is given by. Okay. So what was the equation for neutral point? I should have put. Let's try deriving this. X bar np. Just look at all the equations once and maybe come up with a way to derive this. Are all the terms familiar to you? So x bar np is the neutral point. Xac is xac of the wing. What is Tm alpha f? What do you think it means? It's of the fuselage. Okay, of the fuselage, and this entire thing is the contribution of the tail. This we have seen. We have just not derived this. We have seen this equation. Okay, so now just take a moment, look at all the options, and then we'll try deriving it. Okay, I don't have place to do the derivation here. Let me just a minute. I'll just add a slide. Static margin equal to x bar np minus x bar cg, and this was equal to negative of the slope dcm upon dcl of the entire aircraft. Now if you were to split it up into the various components, you have minus dcm by dcl of the wing minus dcm upon dcl of the fuselage. This dcl, the cl is of the wing. Okay, then you have minus dcm tail on dcl. Okay, so where was the main equation? Okay, so for this wing equation, this is the contribution of the wing. If you were to do dcm by dcl, what would you get? You would just get this momentum, right? Okay, let me just write that down again. So cm for wing is nothing but cmacw plus that momentum, that is x bar cg minus x bar ac into cl. This is correct? Yes. Okay, so if I were to do dcm by dcl, I would get only x bar cg minus x bar ac. Was it ac minus cg or cg minus ac? Okay, correct? Okay, now let's look into tail. If I were to do tail, cm was the Cm naught, whatever the Cm naught term was, we don't have to worry about that for the stability derivation. And then you had what did you have? Yes, you had that VH term. What did you have there? Had VH minus VH eta 1 minus dou epsilon by dou alpha CL alpha tail by CL alpha wing. Correct? The fuselage, we'll leave it as such because that is what is given to us in the equation. Now we substitute these terms back here. And when you have, now when you do dCm upon dCl, you get minus VH eta 1 by dou epsilon dou alpha CL alpha tail CL alpha wing. Okay, now you substitute these quantities into your main equation. What do you get? X bar NP equals, take CG on this side, you get X bar CG, and you have minus dCm upon dCl of the wing. Okay, so what will it be? It will be minus X bar CG plus X bar AC. Then you have minus dCm upon dCl of fuselage, minus dCm fuselage by dCl. Then you have minus dCm upon dCl of the tail. So you have plus VH eta 1 minus dou epsilon by dou alpha CL alpha tail and CL alpha wing. So these two get cancelled, and this is your final expression for neutral point when you consider wing, tail and fuselage contributions. Okay, so this was the wing contribution, this was the fuselage, and this entire thing was the tail contribution. Okay, so what is the correct answer? It is this one. From this, can you tell me if fuselage is it contributing towards static stability or is it destabilizing? We concluded that tail stabilizes, right? Because it contributes towards it makes this xnp minus xcg, the static margin, it makes it positive because it is positive, right? What about this? Exactly, fuselage is destabilizing because there's a negative sign there. Okay, it reduces the static margins value.
Shouldn't it be option D? Because in option C is 1 plus 2 multiplied by.
Oh, okay, sorry, yes, that is the right answer. Correct, it's option D. Okay, so this is negative and this is also negative. Correct, you're right. Okay, so fuselage is destabilizing whereas tail is stabilizing. Okay, let's go to the next question. If an aircraft continues to go farther away from equilibrium position after being disturbed, then the aircraft is called statically stable, neutrally stable, unstable, or none of these. Okay, so it is unstable, right? If it continues to go further away from equilibrium position, it doesn't show any tendency to come back to stability, right? So it is unstable, right? Okay, can a statically unstable aircraft be dynamically stable? And what about vice versa? Can a dynamically unstable? Okay, okay. So in this case, unstable, just saying unstable is fine, right? Okay, so unstable. Next question. A wing-alone aircraft has an aerodynamic center pitching moment coefficient, that is CMAC, of minus 0.096. If lift coefficient at zero angle of attack is 0.28, find Cm0, and they've given you x bar Cg, and assume that the aerodynamic center is at 0.25 Mach. So how do we proceed this? They've asked you to find out Cm0. Take a second to think about it. So is this aircraft, does it have what kind of wing cross section? The cross section of the wing, what airfoil is it? It's positive cambered airfoil. Okay. How do you find out Cm0? Okay, Cm is equal to Cm0 plus Cm alpha into alpha. Okay, then how do I proceed? Cl alpha into xcg minus x. Is this right? Yeah, it should be Cl0. Right? Now does it make sense? Because the Cl alpha will come into this term that is dependent on alpha. Right? So your, okay, let me write this down. It should be plus Cl alpha into x bar Cg minus x bar AC. So this term is your Cm0. Correct? Cm0 is CMAC. CMAC here is minus 0.096. So the someone who said Cl alpha into xcg minus xac, are you clear now why it's Cl0? Okay, yeah. So let's proceed with this. Cl0 is 0.28. X bar Cg is 0.35 and this is 0.25. Straightforward calculation. What is the value? So it comes to minus 0.068. So that is this value. This is Cm0. Okay. So we cannot pitch this aircraft at a positive angle of attack. We require Cm0 to be positive to ensure that you can trim the aircraft at a positive angle of attack. Okay. This cannot be done in this case because your Cm0 is negative. Okay. Let's go to the next question. Aircraft is said to be statically stable if it has an initial tendency to come back to its original equilibrium condition after being disturbed. It has a tendency to return to equilibrium state with the help of the pilot's input. It has more lift than weight always. It has more thrust than drag. First option, correct. This is the first point that we discussed when we introduced stability. The static stability is initial tendency to come back. Okay. Longitudinal stability is about which axis? Pitching axis. Correct. An aircraft wing is experiencing an angle of attack of 5.21 degrees. That is alpha wing is 5.21 degrees. Downwash due to wing is 2.62. So epsilon is 2.62 degrees. Then how much angle is being seen by the tail of the aircraft? So they've asked you what is alpha tail. What is alpha tail? had a tail setting angle? Will it be minus I? Okay, minus IT. It will be plus IT, right? It will be plus IT because uh, suppose your wing is experiencing an angle of attack here. It is reduced by the downwash angle, but your tail setting angle is positive if it's above, right? It will be plus IT. Okay, that's not in the question right now, so let's continue with this. Alpha wing is 5.21 degrees minus 2.62. What is the answer? 2.59 degrees. Okay, let's go to the next question. Which of the following is the correct relation for aspect ratios of wing and horizontal tail? Think about it. Why? Correct, exactly. So even when the wing stalls, if the aircraft doesn't, if the tail doesn't stall, you still have some stability, you still have some control. So your CL versus alpha, if it was initially like this, if for an aspect ratio say 5, when you decrease the aspect ratio, your stalling angle is moved. So you have a longer range for operation. Your stalling alpha is changed. So this was your initial stall. This is your stall now if you reduce your aspect ratio. Okay, so yes, the first option is right. And the tail should stall after the wing, so you have the aspect ratio of the tail to be lesser than the aspect ratio of the wing. Okay, a positive tail incidence angle setting as compared to zero tail incidence angle setting will result in less stability, more stability, same stability, static stability. What will it be? Okay, can you try to justify that? Why less static stability? Okay, okay. Does okay. Does anyone else have any other answer? Okay, let's have a look at the equation. Let's go back. Okay, so we look at the tail contribution. This was the tail contribution, right? Where do you see tail setting angle appearing in this equation? What is the term? It's IT, right? IT is the tail setting angle. Yes. So if I increase or decrease, what was the question? Increase, right? So if I increase the tail setting angle, how will the stability change? If I increase the tail setting angle, will the stability increase or reduce? Think about it, the equation is right here. This is the equation. Will it increase or reduce? If I increase the tail setting angle, will the stability, static stability increase or decrease? What will it be? It will? Yes. Huh. Yes. So will the static stability increase or reduce? Okay. If the value of Cm naught changes, how does it affect stability? For stability, we have only Cm alpha. See, in the Cm alpha term, this IT is not appearing at all, correct? So the IT, that is the tail setting angle, will not help in any way if the angle of attack is disturbed, right? That's what it means. So if I was flying at some 5 degrees and a gust comes and it becomes 5.1 degrees, the tail setting angle will not contribute in any way to bring it back or to take it away, right? The change in alpha, the d alpha, because of IT, there will be no change in d alpha, correct? When there is a change in the alpha, the tendency to bring it back to the original alpha is what we call as static stability. And that is governed by Cm alpha. Cm alpha. But your tail setting angle does not appear in the Cm alpha term at all. It appears only in the Cm naught term. Correct? And Cm naught does not affect static stability in any way. So, sorry, I couldn't hear you. Okay. Yeah, so the change in angle of a tail setting angle or wing setting angle will not affect the static stability in any way. It will only change the Cm naught values. Okay, it will not change the slope. It will only change the intercept. So what it will do is it will shift this line above or below, but it will not change the slope. And if you don't change the slope, it does not change the way the aircraft behaves to a change in the angle of attack. If it was initially stable, it will continue to be stable. If it was initially unstable, it will continue to be unstable. It will not change the stability of the aircraft. Okay, so keep this in mind. Only these parameters, only VH, eta, CL alpha tail, D epsilon by D alpha, X bar CG minus XAC, only those terms affect the stability of the aircraft. All the terms appearing in Cm naught, that is IT, IW, epsilon naught, all of these terms do not affect the stability of the aircraft, longitudinal static stability of the aircraft at all. Okay, so changing the tail, it will reduce the moment magnitude, that is true. But okay, where do I show you? Yes, what I mean is, so from the equation we saw that if the initial graph was like this, and if I increase the tail setting angle, your Cm naught value reduces, right? So it becomes something like this, correct? This is what you're saying, right? Okay. So now suppose we were flying at, suppose this was 5 degrees. So the first condition, this is 1 and this is 2. And then you experience a gust and it moves to 5.1 degrees. Because of this change, it produces a Cm naught, it produces a Cm, right? It produces a Cm that restores restores the angle of attack. Now, the amount of a Cm that contributes to restoration, this dCm, right? The change of moment that is there due to the change of alpha. So dCm due to d alpha will remain same, correct? So the amount of moment that is used to restore the angle of attack is same for both cases, which is how we measure stability. Correct? So the change in moment will remain same. That is all I'm saying. Okay. Okay. So changing the tail setting angle will not contribute towards, where was it? Yeah. So will not affect stability in any way. So same static stability. Go to this question. Look at the graph that is given to you. They've given you CM versus CL variation. They've given you CM naught. This CM naught is not the same as the CM naught for the CM versus alpha. Okay, this is just the intercept of this graph. That is the value that is given to you. Okay. Next, I've asked you to find out the neutral point. How will you find out the neutral point? CM naught will be 0. CM alpha is the slope of this graph, right?
Yes.
That is not 0, right? It's negative. But it's a quantity. What is the slope of this graph? Exactly. So the static margin is x bar np minus x bar cg. It's also equal to minus dcm by d, right? So you can find out the neutral point from here, which is x bar cg minus the slope. What was the slope? 0.078. It will be minus of, correct? The slope is negative, right? Yes. Okay, so this is 0.28. Okay, 0.12. So it's coming to 0.4, right? Okay. So always when they've given you the CMCL variation, the clue that you have is that it represents the slope, gives you the stability. Stability is related directly to static margins. The static margin is the negative of the slope. And static margin, you know, it's the distance between the neutral point and the CG. Okay. So whenever they give you this, just directly try to look at the slope and relate it to what they've asked you. Okay. Look at the next question. Just look at the details that are given to you. The wing fuselage pitching moment characteristics of an airplane are given as. So the contributions of the wing and the fuselage, the combined equation is given to you. Okay. Where alpha is the fuselage reference line angle of attack. And then they've given you the wing parameters, that is the wing area, wing span, wing mean aerodynamic chord, xcg upon c bar, aspect ratio of the wing. Then they've given you CL alpha of the wing fuselage combination. Then they've given you wing setting angle and CL naught. CL at alpha equal to 0 is nothing but CL naught. This is CL naught. Okay. Then they've given you horizontal tail data. They've given you the moment arm, the tail moment arm, aspect ratio of the tail efficiency factor. Tail efficiency factor 1, what does it mean? Correct. Okay. And they've also given you CL alpha of the tail. Okay. Now let's have a look at the questions. Okay. It is desired to have a complete airplane pitching moment characteristic as follows. So the complete equation is given here. The wing fuselage combination is given here. Now the question is the contribution of horizontal tail to CM naught. CM naught tail. That's what we have to find out. How did we come to that? Overall CM naught, and this is the CM naught of wing fuselage. This is wing fuselage and tail. So if you just subtract it, you get 0.2. Correct? So It's right? So it's basically 0.15 minus of minus 0.05, you get 0.2. Okay. Next is a similar question, contribution of horizontal tail to CM alpha. So this was CM alpha whole. Similar to the previous case. So your CM alpha tail is nothing but CM alpha of wing fuselage tail minus CM alpha of wing fuselage. So that is 0.2025. Negative sign was there. Minus of minus 0.0035. Yes. How much was this quantity? Minus. What we can see from here is that the wing fuselage combination, the overall combination, the complete combination and just the tail, they are all contributing towards stabilizing, right? The wing fuselage combination also has a negative slope. The overall CM alpha is negative. It has to be negative for a stable aircraft. But the wing fuselage itself is giving you a negative CM alpha. And therefore the tail is also negative. So they are all stabilizing as far as the pitching moment is concerned. Okay. Next is, what is the approximate value of d epsilon by d alpha? We discussed this formula in one of the slides, in the earlier slides. So d epsilon by, yes. Okay. So E, I don't think is given here. If it's not given, just assume 1. Okay. How do we proceed with this? So it's 2. What is CL alpha of the wing? What is CL alpha of the wing? Of the wing fuselage combination. In this case, they've used wing. Yes. How much is that? 0.07, right? But that is in per degrees. We need to convert it to per radians because this formula is valid only if your CL alpha wing is in per radians, right? Because the final term is dimensionless. So if this has to be valid, this has to be in per radians. How do we convert it to per radians? Multiply. Okay, so that comes to 57.3 into 180 by pi. I will write it. Into 180 by pi. And here you have pi. E is not given, so take it as 1. Aspect ratio is 7.3. What is the final value? Can you calculate and tell me? Point 3 4. Okay. 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 Next question is, if the tail, what is the tail volume ratio? VH. What was the formula for tail volume ratio? Yes. ST. S. Yes. You're converting per degree into per radians. So it is 1 upon radian, 1 upon degree into 1 upon radian. Correct? Okay. Okay. So here, let's see. ST. Of ST. We don't have the value of ST, so how do we find out this? Why will we do that? Huh. Just look at the quantities that are given to you, see what you can find out with it. We don't. SW is given to us. We have this. We don't have ST. Correct? ST is the value that is missing. Okay, can you tell me what was the equation? So you want to use Cm naught of tail, right? Okay, what was the equation for Cm naught of tail that has VH in it? Eta VH. Yeah. Okay, so I think Cl alpha tail is the one, but this should be a Cm alpha of the tail, right? Okay. Cl alpha tail. Correct. So Cm alpha tail we had calculated as minus 0.0215. 215 minus eta is given as 1. VH is what we have to find out. Cl alpha tail. Okay. We have calculated this in the previous thing, that is 0.35. Your Cm alpha tail is also in per degrees, right? Yes. So your VH will give, what will it be? Two one five. Okay, 0.45. Okay, so that is this option. Okay, correct. Okay, next is the ratio of horizontal tail area to wing area. Now we use the previous formula, right? VH is STLT upon SC bar, and we need to find out this. So STS is VH into C bar upon LT. VH was 0.453, 0.453 into C bar was 1.524 by LT is 4.496. Okay, 0.153. Correct. Next, the approximate value of epsilon naught, similar to d epsilon by d alpha. Correct. So what are the values? 2Cl naught is Cl naught is 0.26 by pi 1 aspect ratio is 7.3. What is this value? They've asked you in per degrees, I mean in degrees. Okay, this is value you get here is in radians. Convert it to degrees. 1.3, right? Yes. Correct me if I'm going wrong somewhere.
Your answer is correct.
Okay. Now let's go to the next question. Calculate the tail incidence angle IT in degrees required to achieve CM naught tail. Here we use the CM naught tail formula. In the previous question, here someone had mentioned that we can use CM naught of tail. We could not have used it here because terms such as tail setting angle, wing setting angle are required. Wing setting angle is given to you, but tail setting angle was not given. So you could not have used the CM naught tail. Okay. So now we use that formula to find out the tail setting angle. What was the formula? So CM naught tail was eta VH CL alpha tail into I wing minus epsilon naught plus epsilon naught minus I tail. Correct? So now you know eta, you know VH, you know CL alpha tail, you know the wing setting angle. We calculated this and we have this quantity. Only thing unknown is I tail. Okay, CM naught tail was 0.2. So I tail is 0.2 divided by eta is 1. VH is 0.153. 0.153. CL alpha of the tail 0.073. And here you have to convert it because, okay, it's in per degrees, you don't have to convert it. Okay. 2 plus epsilon naught was 1.3. Oh, sorry. It was minus I1 minus epsilon naught plus I1 plus epsilon naught. Okay. So what was it? What is this value? Since we have this I wing and epsilon naught in degrees, you don't have to convert the CL alpha tail, that is already given in per degrees. Okay. Epsilon naught was 1.3. How much are you getting? Minus 2.7. Yes, so minus 2.7 degrees is the tail setting angle. So you require the tail to be set at a negative angle. Okay, that is when you get the CM naught positive. Okay. Now next question, they have given you some details. They've given you the weight of the aircraft, the cruising velocity, the area, the density at the cruising altitude, aspect ratio. They've given you that the CG and the AC of the wing are at the same point, and it's 0.3. They've given you neutral point. So is this aircraft stable or unstable? Is the aircraft stable or unstable? Stable. Yes. Why? Because your XNP minus XCG is a positive quantity. So your standard is positive. Okay. Then they've given you CMAC, they've given you CL alpha of the wing and tail to be the same. They've given you in per radians. Then they've given you the angle of attack at zero lift. They've given you wing setting angle, tail tail efficiency factor, horizontal tail volume ratio, E, the Oswald efficiency factor, tau. Tau here is control surface effectiveness parameter, okay? And they've given you maximum elevator deflection. Okay. Now let's have a look at the questions. The lift coefficient for cruise is CL cruise. How do you find this? How do you find this? Just look at the data that is given to you. Okay, so you have lift equal to weight, and then you take W equal to rho v square S. They've given you the cruise velocity. So 2 into 2500 into 9.81 by density is 0.85, velocity is 130, area is 60. So what is the value of CL?
Six.
569. Okay. So that's this one. Okay. Next question. The downwash angle at tail epsilon naught is approximately how much in degrees? How do you calculate this? What was the formula for epsilon naught? We used it in the previous question. What was it? By pi EAR. Correct? So what is CL naught here? We have E, we have aspect ratio. What is CL naught? So they've given you the angle of attack at zero lift. Okay, so it's something like this. This is the CL versus alpha curve. This alpha is given to you as minus 2 degrees. And they've also given you the slope of this curve in per radians. So this is your CL naught. How do you find out CL naught? It is just the slope into this 2 degrees, right? CL naught is slope, so it's minus 2, just the value, so it will be 2 into 4.584, but it is in per radian. So what do? This is in degrees. You have to convert the degrees to radians. So there you multiplied by 180 by pi, here you multiply by pi by 180. Correct? So this value is 2 into 0.16. Correct? Now you substitute it here and complete this. So that is 2 into 0.16 by pi. E is 1. AR is, how much is AR? AR is not given to you. Oh, it's given 5. Correct. So how much is this value? Zero point zero 22, correct? And this is in radians, okay? So this equation, both those equations, epsilon naught and d epsilon by d alpha, are valid when all the terms are in radians or per radians, okay? So this value gives you in radians. They've asked you in degrees. When you convert it, how much do you get? 1.16 if I'm not wrong. 1.16 degrees. Correct? Okay. Go to the next question. The value of Cm naught of the aircraft, assuming that the fuselage contribution is 0. How do you find this? We just did it, right? So find the contribution of the wing, find the contribution of the tail, and add them. So Cm naught of the wing, what was it? Cm naught of the wing. Let's just go to that formula. Right, so it was this. Cm ACW plus CL naught into the moment arm. So it is Cm ACW plus CL naught into x bar CG minus x bar AC. So what is Cm ACW? Minus 0.1 plus CL naught was 0.16. But since your CG and AC are at the same point, AC of the wing, this will be 0. So it will just be minus 0.1. Now the Cm naught contribution of the tail. What was it? Eta VH CL alpha tail wing setting angle plus epsilon naught minus tail setting angle. What was it? Epsilon is 0.8, VH is 0.45, CL alpha of the tail, it is 4.584. It is in per radians. Okay. So what do we do here? Into, it is in per radians, into 180 by pi, because our values here are in degrees, okay? So wing setting angle is 3, epsilon naught was 1.16 minus tail setting angle is minus 2 degrees. So how much is this value? Is it 0.1177? Correct? So the overall Cm naught is Cm naught of the wing plus Cm naught of the tail. Naught of the wing is minus 0.1 plus 0.177 as fourth digit here. So you get it as 0.0774. So the overall Cm naught of this aircraft is positive. So you can trim the aircraft at a positive angle of attack. Okay. Is this clear? Can I go to the next question? Just a minute. Here, because these values are in degrees, we convert those into radians. Okay, so this is this cm naught tail, all of those equations are also valid only for radians. That was the mistake that I made. So here it will be pi by 180. You're converting these degrees into radians. Okay. So multiply. Now is it matching? Okay. You have the choice of taking per degrees or per radians when it comes to cm alpha, because those terms get cancelled, right? So, but if it is cm naught, you have to take it in radians. That was the mistake that I made in this equation. So you convert these degrees into radians. Okay. 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 So next question is, static margin during cruise is close to. Static margin is xnp minus xcg, right? xnp is directly given to you, xcg is directly given to you. So static margin x bar np minus x bar cg is just 0.52 minus 0.3, correct? Just 0.22. So the aircraft is stable. Now the value of cm delta E. I'm not sure if control was dealt with in the previous lectures. So I'll just give you the equation. Cm delta E. Was it addressed in the lectures? The recorded lectures? The control terms, the elevator deflection? Okay. 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 So I'll just put up the formula. So Cm delta E is minus eta VH. Eta VH CL alpha tail and the control surface effectiveness parameter. So it's straightforward. Minus 0.8, VH is 0.45, CL alpha tail. Where is CL alpha tail? Okay. 4.584, and tau is also directly given to you. 0.4. What is the value? Minus 0.66. Correct? Okay. Then for a cruise flight, the delta E required to trim the aircraft. Again, I'm not sure if this was dealt with, but since stability control was the prerequisite, you should have gone through it. I'll just write it down. So the elevator deflection required to trim the aircraft at a given CL. That formula we have with us. Delta E trim is delta E naught plus d delta E by dCl into CL trim, right? And they've asked you the delta E trim to trim the aircraft in cruise flight. So we calculated the cruise CL initially. So in our case, CL cruise equal to CL trim. Now what are the remaining parameters? This delta E naught is minus Cm naught by Cm delta E, and this d delta E by dCl is the static margin xnp minus xcg by Cm delta E into CL trim. Then it's just a straightforward substitution. Cm naught is, what is the value of Cm naught? 0.00774. 0.0774. Cm delta E was minus 0.66. Again, this value will give you the deflection in radians, but the options are in degrees. So ensure that you convert that. So this comes to minus 0.07 radians, and in degrees that is minus 4.143 degrees. Correct? So that is the amount you need to deflect the elevator to ensure that you trim the aircraft at the given C. Okay. So with this we come to the end of this session. Does anybody have any questions? So I will address the flare distance in the next week, and I also let the other TA know about the fifth question. But anything else? Okay. So if no doubts, then we'll end the session here. Thank you. We'll meet on Tuesday.
Thank you.
Thank you.